Okay. Okay, and then today's discussion we will go through some of the issues relevant to the memory system. When I say memory, it's off-chip memory. We have been talking about structures or microarchitectural units which are present on chip. So I think I have suggested you to go through the basic 101 level videos on memory and the organization, but if you haven't done that, so this is again 10,000 feet view. So if you have opened up your laptop or your desktop, the entire box that you guys call it, you might have seen this green colored DIMM. It's called a DIMM, dual inline memory module. And the way to look at this particular DIMM is through hierarchy. This is similar to your cache hierarchy where you have lines, sets, and all. Here also the data is organized in the form of various granularities. So the first thing is called the channel, which is connecting your last level cache or the processor to the memory, off-chip memory. And this is the DIMM that you can see on your screen. It has two sides. One side of each DIMM is known as the rank. And so we have two ranks here. And if you look at one side of the rank, you will find this black rectangular boxes, right? So these are actually known as chips, and these are actually the DRAM chips where the data is stored. And each of these DRAM chips are organized in the form of banks, which is nothing but a 2D structure consisting of rows and columns. Okay, so whenever we get a request from the processor, it goes through this notion of hierarchy to get the data from memory, and then eventually it sends it back to the processor. So we will see what exactly happens on a request, but this is the typical hierarchy. So the most important thing that you should remember is that there is something called rank, and which consists of multiple devices that has banks, and bank is nothing but a 2D structure consisting of rows and columns. Okay. So similar to any other microarchitecture structure or any other device for which you are actually sending address and you are expending or expecting data, you will find the notion of buffers or some kind of queues. So here also per bank you will find something called a row buffer, and the idea of row buffer is once you bring a row from one of your bank, you can put it here, assuming it will be reused in the future. Again, locality. Okay. Initially, it will be empty. There won't be anything in the row buffer. And let's say these are the requests that you are getting from your processor. That means you are getting a miss at the last level cache. And there is some address mapping that finally tells you, you have to go to the bank number 0, row number 0, and column number 0. So in this case, as there is nothing in the row buffer, you actually get a miss. Okay. And what you need to do is you need to grab the row from the bank into a row buffer. Okay, so this entire process is known as activate. We're activating a particular row from a collection of rows, and you are putting it into the row buffer. And then after that, since row is a collection of columns, you need to extract a particular column, and that's how you respond back to the upper level. So same thing goes on now. If you get a request to column 1, you get a hit because row buffer contains the same row. So no need to activate again. You can directly do a column read, right? So this goes on as long as you are accessing the same row. Now suddenly, if you are accessing a new row, let's say row 1, which is not there in the row 0, right? So it's actually a conflict. The data is not there, so it's a row for conflict. In this case, what happens? You have to pre-charge, which means you have to keep the content of row 0 back and bring the content of row 1 into the row buffer. So it means this row 0 goes back, and then row 1 comes from the collection of rows into the row buffer. So that is actually known as the pre-charge. Okay, so you're putting it back into the notion of bank, and then you are activating again the new row that you are interested in. Okay, so this is how it operates. The notion the reason I'm talking about all this events is eventually from both security and performance point of view. These events are crucial. Even if you don't work on, let's say, DRAM related topic, it's good to know that your experiments can get affected because of this sequence of events. Okay. There's another thing that I want to mention. This DRAM row is also known as DRAM page. Don't get confused with the OS page. And there are two policies that you can have for the DRAM page. One is called the open policy, which means once you respond a request, let's say for row 0, column 0, you have responded, you kind of keep the row open, right? That means the row first still contains the same row, expecting locality so that you will get future hits. But you can also do the other way around. You can close the row so that uh, let's say row 0, after accessing row 0, you decided that, okay, I'll be using close policy. So you'll put the data back into the DRAM. And next time, if some new row request comes, there is no need to do the pre-charge. Right? You can directly do the activate. So depending on the locality, you will find most of the servers, they go for some form of closed policy or adaptive policy. But in desktop, you will find open policy is widely used because the kind of applications that we use, they are good in locality, relatively more compared to the server workloads. That's how it is. The notion of row of the different commands of interest. There are hundreds of commands that happen when you send a request from last level cache to DRAM, but that's not the goal of this course. So just keep in mind about these three high-level commands. Okay, this activating, pre-charge, and then reading a column. So when someone says, okay, questions?
Sir, in the previous slides, the size of column, is it like one word or one bit?
Sorry?
So what is the size of column here? So one word is equal to one column?
No, the column is typically KBs, so you can expect 4 KB, 8 KB, 16 KB kind of.
Okay.
Yeah. I will show you an example in later slides. But yeah, these are typically in KBs, and the column size will be in bytes.
Okay, sir.
Yeah. So compared to the different microarchitecture structures which are on chip, when we talk about DRAM, the primary goal of DRAM is to provide capacity, so that the applications that you're running, the application should not get page faults. It should not go to the let's say the disk kind of device, right? Hard disk or any other kind of device, right? And so that's why capacity is the primary citizen, which is actually the density. The more and more information that you can store, that is better from a DRAM point of view. That's why latency is not the primary citizen, and that's why you will find the DRAM latency is kind of higher than the on-chip caches and other structures, right? There are various other reasons, but you can easily kind of correlate with the kind of circuitry that is used for DRAM and then the low frequency that is used to operate at a DRAM, right? Then comes the bandwidth, which if you remember, it's the rate at which you can pump data back to, let's say, your last level cache. Compared to latency and bandwidth is actually improving at least from last 10, 15 years. The bandwidth is actually going up at least 10, 15 Gbps in every 2, 3 years, right? And but latency more or less remains the same. Maybe here and there some up and down. Um, Capacity and bandwidth are going up if you look at the trend. And then comes the power, right? Again, depending on whether you are working or designing a server where you are operating on large amount of data, DRAM power actually play a big role because they are kind of power hungry circuits. And then more you go to DRAM, the entire server or data center or whatever you are building on, that will consume more and more power, right? So that is one of the hot topics. at least if you consider the notion of data centers, right? Where your power consumption at the DRAM level or up-chip memory level will be directly correlated with the electricity bill, right? And then comes the notion of reliability and security, which is kind of there before, but there are kind of new attacks. There are new possibilities that are coming in every now and then. Okay. So with that, what I will do is I will just go through the notion of DRAM addressing again at a high level, because this is again needed for both performance and security related works. So let me just quickly show you what I want to explain here. So it's a toy DRAM. Let's say you have a 2 GB DRAM, and the specifics are your DRAM has 8 banks and 16,000 rows and 2,000 columns per bank. Okay. So now with this information, you need to split out the address which is coming from, let's say, the last level cache, right? So here I'm showing two different ways. One is the cache interleaving, another is the row interleaving, right? So if you remember, we discussed, typical cache line size of 64 bytes. That means it will take 6 bits, right? And that's what it is doing. So after the bit number 6, you will see that you're finding the bits that are driving the bank number, which means the consecutive cache lines will be actually mapped to consecutive banks. And I'm not going into the details, but that helps in providing some form of bank level parallelism, which can be exploited if your requests are actually scattered across different banks. Okay. The other way that I'm showing at the bottom, if you go for the row interleaving, here you will find that the row contains 2000 columns, right? So that will take 11 bits. And so the lower 3 bits you can just ignore. It's actually for the byte offset. Anyway, you don't operate on the byte offset level. And so if you look at, you have to ignore the first 14 bits, and then you are going for the bank number, right? So after 14 bits, the bank number will change, right? So which means all the consecutive rows, right? Row number 0, 1, 2, 3, 4, 5, and all. Now they will be actually mapped to consecutive banks, because row number is here. So the moment you actually put the column bits here, that means a particular bank is actually containing a particular row. And if you look at or scatter your request across banks, you will find consecutive rows, right? So can someone tell me the benefits of row interleaving, where exactly it can be beneficial? Are you guys thinking?
So I think when it is accessing multiple pages at a time.
OS pages or DRAM pages?
DRAM pages.
What do you mean by accessing multiple pages in?
Because you want to these 11 bits. So basically consecutive rows here are consecutive DRAM pages, right? So consecutive DRAM pages are in consecutive banks. So if you want to exploit this bank level parallelism, then you may want to. So basically, your multiple pages are in multiple banks, and then
that I agree. You are actually just redefining it. I'm saying, can you give a programming construct which can help understanding?
So if you are accessing data from two different pages, and that will happen quite often in your program.
Okay. Any other pointers here? Just attempt. It's okay if you're wrong or if it doesn't make sense. So ideally, what will be the best policy? Yeah, go on. Yes.
Yeah, can we say that in this case we will get more hits in row buffer?
In this case, meaning in the later case, is it?
Yes, in row interleaving case, because the addresses
Why?
are consecutive. That's why.
Addresses are consecutive, meaning what?
Uh,
Addresses are coming from the processor, right? You don't have control over the addresses that are coming. You are just breaking that address into, the DRAM specifics.
okay, okay. No, in a row, if we consider a row, in earlier case, like consecutive addresses will be like scattered across different
Different
banks.
banks. Yeah. Consecutive
But
cache
in
line.
this, yeah, but in this case, consecutive cache lines will be on the same row, same bank.
No, even in the previous case, it was same row because row is actually at the upper level, right? The upper bits. The only
Okay.
difference was it was going to different banks. Right. So if you, let's say, take address 0, address 64, address 128, in the first case, it will go to, bank number 012.
Okay.
Right. The row remains the same, but it goes to different banks.
Yes, and this row buffer structure is per bank, right?
Per bank, yeah.
Yeah, so in earlier case, all these things will be in different banks. Let's say there is like a array, so
Got
it
it.
will
That
be
I got it.
scattered. Yeah.
So what about the later case?
In the later case, in a row itself, we have these things consecutive. So we might get more hits in the row buffer.
Yeah. So if you remember, it's like, you are going to the same bank, same row, right?
Yes.
So the major differences in previous case, even if you are accessing an array, you are actually going to different banks. Here you are going to the same bank and same row. Now the question is which one will be the faster?
Okay. Yeah.
Assuming this is the access pattern. Okay.
So if there is high temporal locality, like maybe like
Temporal locality here, right? It's all spatial locality.
okay. So what I mean is if consecutive accesses are just accesses to the nearby addresses.
Okay. Yeah, that is actually spatial locality.
Okay.
Yeah. So if you are saying that all these requests are coming, frequently, regularly, consecutively,
Yeah.
then you can also say, yeah, both temporally and spatially they are, localized.
Yeah, so in that case, I think second case might be more advantageous because the entire row is already there in the row buffer, so I can just access a different column from the same row very quickly.
Yeah. So instead of trying to answer these questions, it all depends on the latency for each of these events, right? So I haven't talked about the different latencies that can come in. We just discussed about the notion of this activate, precharge, and column, but there are so many other timing parameters. Okay, and then depending on their latencies, it may happen that for a particular access pattern, row interleaving is better. Maybe for some other cache interleaving is better. Okay. So if you look at the current machines, they don't have any fixed kind of address mapping. Instead, they actually use similar to, if you remember, the LLC indexing mapping that we discussed, some kind of hash that takes bits from here and there, blah, blah, blah. So even here at the DRAM level, so you don't use, something pretty specific or something pretty deterministic. You actually put a XOR here and there and then try to make sure that, the requests are kind of scattered across different banks, different rows, so that some form of parallelism can be exploited. Okay. So the DRAM that, or the DIMM that we have been discussing so far, that is off chip, but there is another structure which is a DRAM controller that is on chip. Okay, it's actually sitting inside your processor that you have along with your last level cache and all. So the moment you get a miss at the last level cache, the address mapping policy that we have been talking about, that is actually present at the DRAM controller. So it will break the address into, the rank, bank, channel, and whatever. Then there are two queues. One is for read queue, which is for all the demand request that is coming from the processor. And there is a write queue, which is essentially used for the write backs, which are coming from the last level cache. But so these are loads and write backs, right? So what this DRAM controller will do is it will break. Yeah, go on.
Yeah, I have a basic question. So when you say column
Yeah.
generally means a set of 8 bits or like what is it?
Yes, it will be 8 bits. Yes.
8 bits. So when we are accessing DRAM, generally one like bit is stored in one capacitor, right? So when
It depends. See, it depends. So what I can have is, I can have a column of yeah, I can actually design a better notion of column, but yeah, for the sake of simplicity, let's assume okay 8 bits. Okay, and then what is your
so
question?
when we give a column address, like
Mhm.
internally is the DRAM organized in such a way that maybe you read one because a bit is stored in one capacitor. So you are reading, let's say, 8 bits at a time.
Mhm.
Like is
So
it organized in that way? I'm
so
not sure how it is.
let
So
me
when we give a
just.
row address and then we give a column address.
I got it. I don't have that animation here, but usually what happens, when you give a particular bank number, right? So you actually go to that particular bank number in all these DRAM chips.
Yes.
Okay. So now when I say go to bank number 0, row number 0, so you go to bank number 0, row number 0 in all these DRAM devices. Okay.
Mm-hmm.
So eventually what will happen? You are actually extracting one bit from one DRAM device.
Yeah. Okay.
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 But eventually, since all the 8 DRAM device will operate in unison, you will get a response of 8 bit.
Okay. Yeah.
Right. So
Okay.
that is like that's how it operates. Yeah. Okay. Yeah. That is there in the previous slide for the architecture course, but I didn't put it here. But hope
Okay.
it's clear.
Yes. Yes. Yes.
Okay. 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 I think, yeah. So I was talking about the notion of different queues. So these are actually the requests which are coming from the processor that got missed at the last level cache. But the DRAM doesn't understand the notion of load, store, write back, and all. So the DRAM has to be you should convert this request into small commands. So commands like activate, pre-charge, and all. So let's say you want to access a particular address XYG, and depending on the address mapper, depending on where exactly it is, you may send a activate command for that, right? That means that particular row, wherever it is present, it will come into the row buffer, right? So you actually populate this kind of commands, the DRAM controller populates, and there is a scheduler similar to any other scheduler that you must have studied in your undergrad or graduate level courses. The goal of this scheduler is to optimize, let's say, latency, fairness, blah, 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 right? And then you can think about a multi-core system where one DRAM controller is shared by, let's say, 4 cores, right? So there are requests coming from multiple cores. You need to make sure that, there is no denial of service, there is no starvation and blah, 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 right? But finally, a simple logic that can be utilized here is, as long as I'm getting row for hits, I can start picking that particular command and then I'll schedule that. Okay. So once you schedule that particular command, it actually goes through this bus, which is called the command or the address bus. It is unidirectional. Okay, you are just passing that command and the address. And the kind of operations that we have been discussing so far, bit of activate, pre-charge, blah, blah, blah. After that, you get the response. And this is data bus. That's why it's bidirectional, right? You can actually write into the DRAM or read from the DRAM. But at a given time, you can actually do one thing. So the modern systems, if you look at what they do is they don't schedule the writes all the time. Only when this queue becomes full or 75% full, then they schedule all the write back requests, and in that time they change the direction of this bus. So the semantic meaning of changing the direction meaning, the control will go from, the control will say that, okay, now data will move from, the DRAM controller to DRAM. And if you are loading something, then the controller will say, okay, you are getting the data from DRAM towards DRAM controller. Okay. It has its own latency also. So depending on how frequently you write, it can also affect your read, and eventually it can affect your latency, execution time and all. Okay. there are few subtle points here. The frequency at which this particular bus runs at, that drives the the latency also. Remember, this frequency is different from your CPU frequency because this is op-chip, right? And all the modern DRAM device, you will find they are actually following a DDR standard, which means double data rate. In a particular clock tick, you can actually transfer data in the both rising edge and the falling edge of the tick. Okay, so that's why this frequency of data bus is always 2 times of the address bus. Okay, that's the high level understanding. Just a high level overview on the kind of bandwidth that you can get in today's DIMMs or the DDR standards. So DDR5 is kind of the latest. It's already there in the market. So if you look at the bandwidth that it's provided, it's around 50 Gbps. Okay, but this is kind of the history that has that is visible here in terms of bandwidth. If you compare, last 10-15 years, so the bandwidth has improved. So this column is showing the transfer rate in terms of mega transfers per second, and every transfer you actually communicate 8 bytes. So since the transfer rate is 6400, if you multiply 8, you will get 51.2 Gbps. Okay, and this is the clock, the data bus clock, where actually you respond the data. And this clock is actually the memory clock, the DRAM device clock, which is clocked at pretty low frequency, mostly for power regions. Okay, so this is how you should look at, if you are, taking a project on security or performance, you will find this particular kind of, specification. So DDR5 6400. So 6400 meaning the transfer rate is 6400 mega transfer per second. And since in one go you can transfer 8 bytes, you can assume, the bandwidth is around 51.2 Gbps. Okay. Yeah. So with that, I'll stop the basic DRAM. I'll jump into some of the advanced topics. Any questions so far?
So what will the memory clock will be used for? I mean, what purposes?
It's again a circuit, right? So you need to clock it to the basic banks and then rows and other things. You have to clock it, right?
Can't you use the same clock? I mean, why
Yeah,
have two
that's what I'm
different
saying. You
clocks?
can use the same clock, but power is one of the major concerns. Okay, there are other issues like heat and other issues are there, but power is one of the major concerns. So that's why you won't be seeing, memory clock is in gigahertz. Any other questions? Okay, so if there are no queries, so let's move to a different way of organizing memory, which is mostly for bandwidth purpose. It's known as high bandwidth memory or HBM. You can just Google it. You will find new DIMMs or there are commercial memory systems that actually provide this HBM. Even Intel has that. And the crux or the difference that we have with HBM compared to the previous DDR standard is, the DRAMs that we have been discussing so far, that was op-chip. You have to go to the DRAM, get the data. There's a latency bandwidth bottleneck. With HBM, it's actually using something called a 3D stacking, where the blue color, the base layer, that's actually your CPU, the logic. And then you have stacked all your, DRAM modules one after another. And they are connected through something called through silicon via, which is TSB in short. Okay. So the primary reason for coming up with this particular organization, which is completely different, is to provide, high speed or high bandwidth. So I talked about, DDR5, which is providing around 50 Gbps. So if you look at the latest HBM, that provides around 800 Gbps. Okay, so here B is actually capital B. Okay, So servers or maybe machines which are used mostly for gaming, or anywhere you need more and more bandwidth. Let's say GPUs, which are actually mostly bandwidth starved, not latency starved. Thousands of threads sending requests to the memory to get the data. HBM is a good alternative, right? And the obvious downside of HBM is the capacity, because you are using most of these resources to get the data faster. Okay, so your goal is not density here, right? So you should not compare HBM with the DRAM saying, okay, that guy can go up to TB and then provide 50 Gbps, but here you are giving only 24 GB. But that's the difference here. The goal is not to provide huge memory. The goal is to provide high bandwidth. Okay. If you look at from the research point of view, which is kind of the theme for this course, there are many topics like DRAM address mapping techniques, scheduling. Can you come up with fairness, conscious DRAM scheduler, DRAM controller? All these things are heavily done in last 15-20 years. Okay, and then you will find it's extremely hard if you want to come up with a new idea, especially in these topics. Okay. Having said that, these problems are not solved. For example, DRAM scheduling is still a point of concern if you are talking about many core systems, right? So if you take 64 core, 128 core systems, where typically you will find one controller is mapped to, let's say, 4 to 8 cores, right? So that means there are 10 DRAM controllers and then there are 100 cores, right? And they are kind of fighting with each other to get the data from DRAM. So there, the scheduling is still a major bottleneck, and then that is still an open problem. It's not like it's done, it's solved. Just that the community has moved away thanks to HBM. So every time now you write something about bandwidth, they say, okay, go for HBM, right? Why to improve the bandwidth of DDR? So these are the different trade-offs. I'll slightly digress and then try to pitch for a different way of looking into the memory and then the computation or the communication between the computation and the memory. So this is something from Google data center workloads. You can find Gmail, different search and blah blah blah. The pretty common chart that we have seen even during last week, right? So most part of the time you are actually spending time in the backend. Remember the backend of the processor where you actually send requests to the cache hierarchy, TLB, and blah blah blah. So you can find that more than 50 to 60% of the requests are actually going to the backend, and that is the bottleneck in all these data center workloads, right? And if you think about the energy or that can eventually manifest in terms of power, just look at the unit used for DRAM read write and then others, right? So others are in picojoule, and then DRAM is in nanojoule, right? So you can easily correlate, the simple operation that you do in processor compared to if you are going to memory. In terms of energy efficiency, it is 1000 times worse. Okay, and then since this kind of trend was there, it was not a big deal. But now that people are talking more and more about green computing, sustainable computers, sustainable data centers, blah blah blah, all these numbers actually play a big role, right? And that's where the motivation for a new way of communication between processor and memory comes up. So again, this is for a mobile device. So you can find it in your mobile phone. If you have a smartphone, you'll find multiple CPUs, GPUs, cache hierarchies, other small IPs, your display, video, encoder, decoder, audio, maybe camera, and blah blah blah. And finally, you go to DRAM, because that's how it is. That's how it's designed, right? For anything, you have to go to DRAM. So one interesting thing that you can take it as a project if you want to do it for the course is how can you allocate, or how can you schedule or allocate your bandwidth among heterogeneous agents. So here the agents are, CPU, GPU, different audio, video encoder, decoder, display engine. There may be some other IP engines. You can take a latest phone from Google, right? You will find there are many other things that are there, right? And again, energy is the bottleneck. And if you can think about your mobile battery power, you can correlate with, this as the bottleneck. So the more and more your requests go to the memory in your mobile, your battery drains fast, right? So with that motivation, at least in the academic research and in industry, initially they came up with the notion of processing in memory, which is kind of a bit far-fetched idea, but I'll be talking about something which is like processing near memory. Okay, and this is already commercialized. It's not like I'm talking about something which will come in the future. So the idea of processing near memory is, so you can see, buffers inside the DIMMs, right? And these buffers have logic embedded in it. Logic meaning basic, some simple functionality. They're already there. So it's like a small toy processor that can do some specific operations, right? In that case, there is no need to go back and forth between your processor and memory, even for a simple load, for a simple computation, simple art, which is involving memory address, right? But the challenge here is, let me just show you how it looks. You actually put a compute unit or logic in memory or near memory. Okay, mostly it's similar if not the same, but the challenges are in terms of who will decide which particular computation will go to the processing in memory unit, or how do you code your program such that that particular part of the program will go to the PIM? Because right now the way you code, it's like, okay, CPU will take care of it. It's a black box, but that won't happen with this, right? Because now you have a lightweight processor sitting somewhere closer to the memory. So you need a hardware software co-design in the form of a bit of support from the software side, saying, okay, these are the new instructions that you can use as a programmer if you want to exploit the processing near memory capability, right? And OS also has to come into picture, because remember the notion of virtual memory. Now, how exactly you'll define virtual memory if your processor is sitting here, right? So we will take few ideas in this course, but for the today's lecture, we won't go into the detail. At a high level, this is the idea, where you kind of delegate few of simple computations, but which are happening regularly. You can take an example of any ML application, right? That operates on, let's say, matrices, right? And mostly the computations are multiplication, addition, or something like that. So for that, there's no need to go back and forth between CPU and DRAM. You can actually put a small compute unit which can do the job for you, right? So that's what it is, the PIM or processing near memory. Before I wrap up the performance side, another interesting thing that has come up recently, again, it's there if you buy a new new DIM, there's a possibility that you can buy a Intel Optane DIM, which is actually non-volatile memory. So by default, when someone says memory, it's volatile, right? So the way we have learned our memory hierarchy lectures in the undergrad, but things have changed now. And if you buy this Intel Optane, it actually gives you two different modes to operate. So one is called the application mode, where it's non-volatile. That means even if the power goes up, the data still remains in the DIM. Okay. And as a programmer, as OS, you can decide, where to map your data, what particular operations to do, and at what granularity to do the job, right? It usually provides byte level operations in the application mode, right? But if you don't want to go for this application mode, you can go for a memory mode. So the memory mode is volatile, as usual, the old world. And here what happens is the capacity of the Intel Optane, right, which was supposed to be operate as a non-volatile memory, that becomes a cache. So you can assume this is like your L4 cache now. Okay, but instead of SRAM, it is designed using DRAM. So now you can imagine your L4 cache having GBs of data. So here programmer has no control because it's a typical memory hierarchy, just one more level in terms of L4, which is designed in the form of a DRAM cache. So if you need more capacity, you can go for memory mode. If you need persistency, where your data should be persisting even across different boots of the OS, or even if the power goes down, or even if something happens, the data should be there in the memory, then you should go for the application mode. Okay, going forward, people are also talking about making the last level cache non-volatile, right? So that means even your memory and your last level cache both will contain the data even if you switch off your machine, right? The downside of all this technology is the latency and bandwidth is extremely low. So if you have a modern Intel Optane memory, you can compare that the DRAM bandwidth, which is there for a volatile DRAM, let's say that is 50 Gbps. This Intel Optane will give you, let's say, around 10 Gbps. Okay, and in worst cases, it can give you 2 Gbps or something like that, right? So that is the I would say the trade-off that you want to play with. Similarly, the latency also goes for a toss, and that's how it affects the bandwidth. For a given load, let's say a typical DRAM takes let's say 100 cycles, now it will take 400 cycles, right? So that manifests in terms of bandwidth. You pump less and less data in more and more time, right? So yeah, so these are the some of the hot topics or which are kind of emerging topics that as a programmer you can exploit, you can explore, you can optimize, or even as a micro architect you can try to find out what is the best way to organize this memory. So remember, you can also have a heterogeneous memory where something is completely volatile, something is completely non-volatile, something is in between. And then as an OS or as an application, you can have a runtime system that decides, okay, which application to map to which memory, right? So all those possibilities, because now the search space is kind of broad enough, right? You have more and more data to play with. Okay, so with that, I will pause before I jump to the security. Any questions?
Sir, one question. These RAMs have a refresh latency also, right?
Yes, yes.
So, do this refresh latency increases with the capacity of the RAM, or?
No, so okay, so before I answer how it affects, so for the uninitiated, so DRAM devices are mostly capacitor driven, so that's why you need to refresh. Otherwise, they leak. Okay, so eventually the voltage level will go down, and eventually you will lose the content, right? So every few fixed time interval, let's say a few milliseconds or whatever, just for an example, you have to let's say refresh, right? And the refreshing mechanism is actually itself is a research problem, right? How frequent you refresh, how do you refresh, whether you refresh all the rows within a bank, or you refresh specific rows among different banks and all, right? So usually, if you look at the state of the art, they try to make sure that the refresh overhead is kind of minimized. So they come up with scheduling mechanism in which you can actually schedule refresh commands to some bank and some rank, and at the same time schedule some of the loads. Okay. And the answer to your question is if the capacity affects your refresh latency, it depends how are you scheduling your refresh, right? At what granularity you are doing your refresh, right? So if you say that, okay, my refresh will actually, read one row at a time, starting from row 0, 1, 2, 3, 4 for each bank and each rank, then yeah, obviously it will take more time. Does that make sense?
Yes, sir. So it might be like if some people want to reduce the speed, they might want to have like whatever are the latest rows which have been written, and so they don't need to be refreshed. But the rows which
Yeah,
have not been.
you need a bit of heuristics to decide, how to schedule refresh along with your normal requests that are coming from the processor.
And one more, when let's say refresh basically a rewrite, right? I mean,
Yeah, so yeah, so when you say refresh, it means you are kind of, making sure that the voltage level is actually crossing a threshold because of which the data still is present and it's a valid data, right? So it's a basic combination of activate precharge, nothing else.
Okay. Okay. Activate and precharge will simply refresh that particular.
Exactly.
capacitor.
That's right. Yes. So I am giving you a CS level definition of activate precharge, but if there are EE students, they will be able to understand what exactly activate precharge means. I'm not talking about the voltage lines and other things. Any other questions?
Yeah, sir, about the NVMs.
Hmm.
So NVMs have a lot less bandwidth than normal, usual DIMMs.
Mhm.
So, like, why should we even consider to use them as L4 caches? We can just
No,
use.
so no. The bandwidth will be low if you need non-volatility. If you are not considered about persistency, then that will become your L4 cache. Okay, and then that doesn't provide persistency now. It's a normal DRAM cache. So the utility of using persistent, non-persistent but L4 DRAM cache is the capacity is huge. Now you won't go to DRAM frequently.
Okay, got it.
Okay.
So in case of the volatile mode, we can do that.
Exactly. Yes.
Okay.
Yes. Yeah. So ideally, I should actually show you all these things, by running programs on a machine with Intel Optane. Thanks to online mode, I don't think anything is possible. I don't have enough machines, or forget about enough machine. I don't have a machine that has Intel Optane. Maybe I can check with others, but if you have, feel free to try it.
Yeah, so another question about the processing in memory. So I don't exactly understand how like moving these instructions to the DRAM will result in performance improvement.
No, it's like, let's say you want to do a matrix multiplication, right? Now what you do? You do load A0, load A1, load A2, load A3, right? And
Right.
then finally you do A0 into A1, something, right? That's how you operate.
Yeah.
Now with this, you are saying that, okay, I have a simple multiplier or adder here, sitting here, right? So I will do A0, A1, A2, whatever is needed. Finally, once it is done, I will delegate to CPU that this is the final output.
Okay.
Right? So I can, depending on the size of the matrix, now I can actually improve my performance in X, right? 10x, 15x, 20x. Yeah, but it's not that straightforward. I'm just giving you a hypothetical example. There are other trade-offs, but this is the high-level utility.
Okay. For that,
So is this
we can use a parallel architecture structure, like
Parallel architecture meaning?
I mean GPUs or something like that. Too.
Yeah, but again, GPUs will get the data from DRAM only, right? So let's say you have a matrix multiplication of 1 GB size. Even GPUs will take time. Go and try it out.
Okay.
So is this similar to the I/O that happens, the reading from disk that you do? You just let the disk read it, and once the reading finishes, then you get to know, okay, this is the final data. Is this similar? Like you just uh, give the computation to DRAM, the DRAM finishes it, and then you get it. And till then, the CPU can do processing of further instructions.
No. It's not like that. So there, it's like, you're kind of delegating the work, and at the same time, you're doing something else. Although you can do the same thing here, but here at a runtime or at a programmer level, you should be clear that what are the chunks of your code that will actually go to the processing in memory. Okay, so maybe that will be much more clearer once we take a latest PIM paper and maybe try to run or try to discuss how an ML training can be done, or maybe a graph processing can be done. Then only it will be much more clearer.
Okay, sir. Yeah.
Right? Yeah. So I will actually float those kind of papers. Let's say you want to do a BFS on Facebook graph, right? That's a huge amount of data, right? The data set will be huge. Now, every time you have to go to memory to process, right? So how PIM can help? We can actually read those things. Okay. Any other query? Otherwise, I will jump into the security part.
In case of the Intel Optane, how the, I mean, is it like a static decision to make the Optanes volatile or non-volatile, or it's like dynamically as per the applications?
No, there are actually two modes available as a programmer for you to decide. You can actually set it when you, let's say you are using your server or whatever, right? With Intel Optane support. So you can set it up before running. It's not dynamic.
Okay.
Yeah.
So for all the applications, once it is set for all the applications, it will be the same, right?
Yeah, so it's like, okay, whenever you want to run it in a volatile mode, you can switch it back to volatile again. Yeah. But in the middle of the application, it won't do both volatile and non-volatile.
Got it.
Yeah. Okay. Into the security issues. So we have been talking about the notion of rows and row buffer, and we have been discussing the notion of various timing channel attacks, and that are mostly possible because two different processes are sharing a particular shared resource, right? So the same thing happens here. This is a particular row, and it may happen that two different processes data is actually, it's stored in a given row. If you try to correlate with the address mapping that we had, right? So it's highly possible that multiple processes can have the data in the same row. And depending on the size of this row, let's say this row size is 16 KB, but my OS page is 4 KB. So depending on the address mapping that is used by the DRAM controller, it's possible that four different processes address and data is mapped to the same row, right? And once you have this kind of setup, then you know how to play a game, right? You can come up with the side channel attacks with the difference in row for hits and row for conflicts, right? So but here it will be more noisy compared to last level cache, because now you have to flush out the entire cache hierarchy or thrash out the entire cache hierarchy, then only the request will come to the DRAM. So in terms of the bandwidth, these attacks will be noisy, and then the bandwidth rate will be pretty low, relatively low compared to the on-chip cache attacks or other attacks, right? But you can play a game. Can someone suggest like how can you mount a side channel here? On the basis of what we discussed, there is a row offer and we do activate precharge. And let's say this is the setup. There are rows which are accessed by both victim and spy, and there are rows which are accessed by only victim or only spy. What will be your sequence of commands?
So, sir, actually, I think if there is a page hit, say spy process is seeing a page hit, that means the victim in that open row or victim process is mapped to that open row, right?
Okay, so basically what you need to do is you have to make sure that you have first created a row conflict, which means as a spy, I will bring, let's say, row R0 here. Okay.
Right.
And then let's say I pause, I wait, and after some time I send a request to, let's say, row R2. And I got a hit. That means the row R2 was, it was activated by a victim.
Right.
Yeah, it's pretty simple, trivial actually. There's no big deal here. Okay. So yeah, similarly, you can actually create a covert channel if you want to communicate ones and zeros, right? What you can do is you can actually make an agreement with the process with whom you want to communicate the data, even if you are not supposed to, based on the latency here, right? You will say that, okay, if you get a row for it all the time, that means I am trying to communicate one. If you are getting row for conflict, then it is zero, right? So again, the bandwidth will be a concern, but still, theoretically, you can mount an attack, and even non-theoretically, you will be able to leak few bits, if not, GBs, right? So that's how it is. I don't want to get into these things because this is same as CAS, right? CAS hit, CAS miss, or row over hit, row over miss. That's the difference. No big deal. What I
Sir,
want to,
uh,
yes, go
one
ahead.
question, but for all this to work, like uh, the attacker should know at least some amount of information about how rows are arranged or what
Exactly,
processor are stored.
exactly,
That
exactly,
information will be very much vital for this, right?
exactly. So similar to the LLC indexing, right? We discussed,
Yes.
the LLC slice number, set number, how they are mapped. So there are papers they have reverse engineered the latest DRAM controllers,
Okay.
especially from Intel again. And now it's kind of open, so you can actually write code and you can check it on your machine. So there are source code again to mount attacks on DRAM. You can see latency difference. Basically, you will find the latency gap between a row for hit and a miss, keeping let's say caches aside. So you have to make sure you are using CL plus frequently, so that
Yeah, yeah.
there is no chance of getting a hit at the cache, and still you will be able to see a difference, right? But yeah, I agree. So you need to have this information. So that's why before proposing these attacks, they actually propose solutions to reverse engineer the address mapping policies.
Okay, okay.
Yeah, yeah.
So it seems that most of the Intel chips, if they can be reverse engineered, security is at risk. Like, and
Yeah,
Intel
yeah.
people already know what their chips have, so the security is quite feeble of the world, right? I mean,
But trust is also a word, right? So like let's say whoever has designed that particular CAS, prefetcher, DRAM controller, whatever, you would expect that he won't open his mouth in public, because there will be usual some legal procedure that goes through when you join a company. But yeah, strange things happen,
okay.
and yeah, so whatever you are thinking in, those things happen regularly. At least if you go to Silicon Valley, you will find folks move from one company to another, and then this kind of information get leaked. Okay, so let me jump into something new that we haven't discussed so far, and it's on integrity. If you remember, we started with the CIA property, confidentiality, integrity, and availability. We have been talking about confidentiality while mounting a timing channel attack, looking at the differences in the latency and all. But there is an attack called Rowhammer, which is affecting your integrity. That means you are writing or you are affecting the content of particular address where you are not supposed to read it. Forget about updating it, right? So since we know the notion of rows in a DRAM organization, so the attack row hammer is you kind of hammer a particular row again and again. Okay, and then the actual technical meaning of hammering is you access that row again and again, right? So that's what row hammer is. And what happens if you kind of access a particular row again and again, because of various reasons, the adjacent rows get affected. When I say affected, it means the content switch from 0 to 1 or 1 to 0, right? And then this is extremely important because now think about big organizations where the medical database is there, or maybe the bank database is there and all, right? And if a few bits get flipped, then that's all right. That's the end of the world, right? At least for a few folks, if not for the entire humanity, right? And that's what the capability of this attacker is, right? It's a attack that doesn't try to eavesdrop and try to find out, okay, what are the possible addresses or what are the possible secret keys that the victim is trying to access, but you actually go and then do something pretty random which affects the victim here. Okay, so that's the high level idea. uh, the terminology that is used by the attackers is that you have an aggressor row where you are kind of continuously accessing that row again and again frequently, and in terms of the physical organization, it starts affecting the victim rows. Oh, this is a famous quote that maybe you can read it later if it makes sense to you. Okay. Let's look at in terms of code what you need to do. So as I've been saying, you have to access a particular address, making sure that there is no cache hit. Because if you get a cache hit, then the request won't go to the DRAM, and that means the row won't be hammered frequently, right? So one thing is CLFlush has its own utility here, right? So if you are a Rowhammer attacker, then CLFlush is the first tool for you. You need to use CLFlush frequently, right? And so that the notion of using CLFlush is you won't get a hits either in the cache or in the row for kind of. So you kind of try to access the same address again and again. But to prevent row overhit, what you can do is you can actually access another row. So instead of hammering one row, it's suggested that you hammer two rows, right? So you hammer X and hammer Y, and then you flush both X and Y. So in this way, what will happen? You won't get those two requests or two addresses in cache, and even the row offer will be confused, right? It will store X and then Y, then X and then Y. That means there will be row for conflict all the time, and there will be cache misses all the time. And this is the entire code. That's all. This is the attack, right? So you are inside a loop. You are accessing two different memory addresses, and you are flushing it. That's what it is, right? So you are loading it, and then you keep on, you're just trying to access again and again, and that affects the nearby rows. Okay. One of the reasons for this attack is the electromagnetic coupling. Again, doubly folks will be able to answer better compared to me, but at a high level, the idea is the DRAM cells are becoming smaller and smaller. Okay. And which means, now if you try to access a particular word line again and again, so word lines are nothing but, if you remember your digital logic course, the notion of word line and bit line, right? Which actually stores your final 1-bit information, right? Where you connect a bit line and word line and you get a 1-bit, right? So if you try to, access frequently those word lines, then there is a disturbance in terms of the voltage levels, and that affects the the adjacent rows, making some kind of disturbances. Let's say the bit will be flipped from 1 to 0 or 0 to 1, and that's what it is. Okay. There are some other reasons, but this is one of the primary reasons because of which it happened. And even in the today's world, this attack is still active. Okay, it's not like that there are mitigations and this attack is done and dusted. Though the news articles that I'm showing are a bit old, but even this is an open problem, and if you can come up with a mitigation technique that mitigate this Rowhammer attack, it will be a big deal for both industry and then in the research world. So just 2 days before, I don't know if you're following all these attacks, there's a new attack that came called Spec Hammer. So it actually, mixed Spectre along with Rowhammer. So now it's a two different gadgets, right? So Spectre, if you remember the if condition, then bound checking, and now they have connected that with the Rowhammer gadget so that speculatively you can now, jump to address which you are not supposed to jump, and also hamper it. So the normal Spectre attack was just affecting your confidential, right? You are able to see what the other process is doing or accessing. Now you can actually affect the other process, right? I will put this paper as a reading material sometime later. I haven't read it yet, but this is the high level abstract that I have read so far. Okay, so yeah.
One question. So there have been some mitigation techniques which can detect attacks which use evictions, right?
Yes.
So this Rowhammer attack can be detected using those techniques, right? Because Rowhammer is evicting
yes
often. Okay.
Yes, and then how will you mitigate?
Like we will just be able to detect, and after that the OS has to take some action once it has detected that this user is actually doing something mischief or something.
Yeah, it's actually pretty subtle, right? So the notion of detection and what you do after detection. So you will find plenty of papers that we'll discuss in next 1 month or so. It's not that simple what we are discussing now. that we can tell OS to, do something to this guy, right? This guy this guy seems like a, attacker or a spy. It's not that simple. We will see why, right? But any mitigation techniques that you can think about mitigating Rowhammer? Maybe we can discuss for a minute or two before I jump in. What can you do to mitigate Rowhammer? Any trivial approach? So Google has tried many ideas. There are academic papers that are there, but still it's open. Even the latest DRAM DDR controllers, they are affected by this.
Keep one process open which accesses all the rows again and again.
That will affect your performance big time, right?
Oh yeah, certainly. Yeah.
Yeah, so one simple approach can be to scatter the accesses to a particular row somehow.
I didn't get it. Scatter the access to a particular row.
Yeah, so whenever the memory controller gets an address.
Try to understand the problem. The problem is right now the attacker has the luxury to access one row again and again frequently in a small amount of time.
Like
you have to prevent that.
Some sort of a timeout, like.
Some sort of timeout in the form of what? How will you ensure a timeout?
Like interval, some interval के उसके बाद he can't access. That must be the gap between the access.
Yeah. So those are the initial ideas when the mitigation techniques came, right? They said, okay, there is a threshold. Let's say the value 10, right? Within a few thousand cycles, few million cycles, if you cross 10, then that's all. You are not allowed to send a refresh. So the DRAM controller won't schedule your refresh, or it won't schedule your, the activate or precharge command to that particular row. Okay. So these are the things you can actually put it in the DRAM controller saying, okay, if this is what is happening, then this is actually Rowhammer happening. Don't schedule anything to that particular row. Okay, but there are folks who try to break this kind of mitigation. So we'll see that through this course. So it's a cat and mouse game, and it's still open.
Sir,
so this will require a counter for each row, right?
Kind of.
Okay. So will that be a hardware overhead?
Obviously. Nothing for free.
Yeah, so sir, refreshing adjacent rows, will it mitigate anything, or
it will mitigate, but even refresh overhead will affect your application.
yeah, it will affect the performance, and you need counters to threshold hardware overhead. All these things will be there.
Yeah. But yeah, that's a feasible approach, because if you refresh frequently, then even if the voltage level goes down, you have refreshed recently, so the data will be still there in the rows.
Yeah, to flip it has to be like the voltage has to be significantly closer to the switching.
Yes. Let's say the BDDY2 threshold.
Yeah. It should be closer to that. Okay.
Yeah. Okay, any other comments, suggestions? I'll just take 5 more minutes and we'll be done.
So maybe tracking the victim rows and mitigate using dummy command like dummy activate of the close to the victim. Those who are close to the threshold value. Something like that.
Yes. You can do all this. Yeah. It's possible. Yes, you can do. See, these ideas, as you can see, right? Even you are coming up with all these ideas, but the trade-offs are the key.
Right. So it can increase the area in memory controller or something.
There are so many other things. What exactly happens to area, storage overhead, energy, power, performance. And then finally, can you give a guarantee that it will be able to, make sure that the Rowhammer never happens? Or you are probabilistically saying, okay, that now instead of 90%, now I'm giving you 9% or 0.9%, right? So yeah, so these are the things that we'll discuss over the next few months. Okay, so let me just quickly jump into the last part, which is called the cold boot attacks. Again, ideally, I should show this on a lecture hall, but again, not possible. If you want to play it with your laptop, do it. So the cold boot attacks are nothing but, you remove your DIMM from your laptop, desktop, or whatever. make sure that you freeze it. Maybe use liquid nitrogen, right? So if you are on campus, you can go to chemistry department, get liquid nitrogen, make sure that it's completely frozen, and then you can actually put it back in any other machine, right? So and then try to access the data, try to dump the entire memory basically, right? So this is actually an attack that was done on a real machine, and this is the outcome. So even after 5 seconds, the content of a particular image, which was there on DRAM during the process of freezing, after 5 seconds, you will be able to, retrieve it almost completely. After 30 seconds, it fades away, it goes away a bit, but still good enough. Even after 60 seconds, you can guess that, okay, this is the image, right? It becomes worse after 5 minutes. Okay, but 5 minutes is actually, if I have to put it from the security point of view, that for 5 minutes your memory is vulnerable, then think about the data that is stored in big organizations, right? And another thing that I want to emphasize here is this is on volatile memory, which on after power off the data goes away, right? And as you can see, within 5 minutes, it's more or less it's kind of non-conclusive, right? You can't inconclusive, you can't get anything out of it. But think about the non-volatile memory now, because the job of those non-volatile memory is they will keep the data, right? And now think about the security issues that will come with the non-volatile memory. So these are actually known as data remnants attacks. Even if you are switching off your machine now with the non-volatile memory, the data are still present in that, let's say, Intel Opten. Right now, you have to just put it back into one of the DIMM slots in another machine, and yeah. So there are other ways to mitigate it or make sure that no one can get the information, but fundamentally at a high level, these are all vulnerable. Okay, so that's the key here. I'll stop. If there are any questions, we'll take it. Otherwise, we are done for the day. So Devasis, you may stop the recording now.